So here again is another observation that you can make in nature that just demands a quantum type explanation. And this is the explanation. There are only certain allowed energy levels for electrons in an atom. And here are the energy levels, let's say, in hydrogen. When you have hydrogen is just a proton and an electron. When the electron is infinitely far away from the proton, we'll call that energy 0. Now, due to the electric potential energy between the electron and the proton, the electron, the lowest energy that it can have is minus 13.6 electron volts. Okay? And then the next highest one is minus 3.4. These electron energy levels correspond to this formula here, minus 13.6 eV divided by n squared. 13.6 eV is usually called the Berg Constant in honor of Rydberg, who first came up with this magic formula for describing the wavelengths of the emission lines from hydrogen. Now, if we imagine that we have an electron in the second highest state decaying down to the first, the lowest energy state by emission of a photon, and calculate what that energy is, it's on the order of 10.2 electron volts. Well, from our formula, remember, 1240 electron volt nanometers divided by the wavelength is that. You can get the wavelength just by dividing by the energy instead. So 1240 divided by 10.2 gives something on the order of 120 nanometers for the wavelength, right? You can do that one in our heads. 120 nanometers is far away from the visible spectrum, which cuts off around 400 nanometers. It's in the ultraviolet. And in fact, all of the emission lines from n equals 3 or 4 or 5 down to n equals 1 are called the Lyman series. They are ultraviolet radiation. When we had this hydrogen discharge tube here on, what you were seeing, the red, the green, blue, and purple lines are in the Balmer series. And that's transitions between n equals 3, 4, 5, etc., down to n equals 2. So when you have a discharge tube like that and you're passing a current through it, you get all sorts of transitions between all these different energy levels, but the ones that are producing visible light are in the Balmer series here. With this formula, we can calculate the energy corresponding to Ne2 levels. And what was demanded is why do electrons have discrete energy levels to begin with? Now, Niels Bohr, the famous physicist in the 20th century, became most famous during the development of the atomic bomb and nuclear physics. He was quite opposed to doing so, but that's another story altogether. Came up with a model for hydrogen in the period around 1910 to 1920 in there, based on the discovery of the nucleus and so forth. And he said, look, electrons are going to orbit a proton like a little planetary system at specific radii. And those radii correspond to multiples of h divided by 2 pi, which we now call h bar. All right? And the lowest energy level corresponds to 13.6 electron volts. In fact, this falls out of demanding this. So this is a theoretical hypothesis that you take Planck's constant and multiples of Planck's constant give you, if you work out the math for the Bohr model of the atom, those radii, the lowest one, lo and behold, corresponds to 13.6 electron volts. It was actually a bit of a miracle that this worked out. This ultimately was not the correct explanation for how the atom is structured, but the Bohr model certainly accounted for these different energy levels inside hydrogen. It was a great triumph in that sense, that you had some sort of picture of how the atom was structured. Now that we knew that the atomic nucleus was so small that the size of a proton, let's say, was so small, you could begin to unravel why electrons had only certain energy levels. Now, where did this h over 2 pi thing come from? The idea was that if you imagine an electron going around in the circle, he was using the idea that the electron could act kind of like a wave, and you want the wave to close on itself and become sort of like a standing wave going around the proton. Well, that's a kind of a radical idea, a standing wave. Heisenberg, who was Bohr's student, really tried to put this on a deeper mathematical footing and said, look, there's a duality that particles like electrons, little things that have mass and charge and travel through space, act not just like little balls bouncing off each other, they act like waves, right? They act like waves and like particles. And French scientist de Broglie further hypothesized that, look, if it's a wave, it's got to have a wavelength. What is its wavelength? Well, it's related to its momentum, p. So you could say lambda is h over p, or p equals h over lambda. The momentum of a particle is related to its wavelength, like so. Possibly one of the simplest equations ever that resulted in a Nobel Prize for this idea. But it led to the whole foundation of what we now call quantum mechanics. And just a few years later, in 1926, Erwin Schrödinger, who had a tough time when he was a young adult deciding whether or not he would pursue a career as a concert violinist or as a physicist, made the right choice and wrote down this equation. It's a wave equation describing an electron wave, right? And you can solve this equation in the case where that electron is trapped in orbit around a proton. And it's one of the calculations we have all of our physics students do when they're a junior or senior. And it's a long, detailed calculation to solve for psi, which is the pattern or the wave pattern of an electron in orbit around a proton. But you can do it. It's a complicated equation, obviously. And at one point, there were only a half dozen people in the world who even knew about it or realized the incredible importance of it. But that was when quantum mechanics was really born and put on a solid mathematical footing. Now I'm going to have you show you a little bit how complicated these calculations can be. Okay, so I'm going to give you plenty of time to do this calculation. I've been doing a lot of talking, so we have an electron accelerated through a 100-volt potential. That gives it a kinetic energy of 100 electron volts. Now, we want to convert electron volts to joules, so we have to multiply by 1.6 10 to the minus 19th joules per electron volt. And you remember, kinetic energy is 1/2 mv squared, right? So we can write that P, the momentum, is square root of 2mk. The mass of the electrons, 9 10 to the minus 31. So you take 100 times 1.6 10 to the minus 19th times 9 10 to the minus 31 times 2, square root of that. And that's the denominator in lambda, for lambda equals h over p. So this is using the de Broglie hypothesis for the wavelength of a massive particle, relating it to its momentum.